Hello everyone, welcome back to another lecture video for Math 110, Introduction to Number Theory. And in this video we're going to talk about Fermat's little theorem and Wilson's theorem. In previous videos we've been talking about congruences modulo n and also manipulating these and solving linear equations. So what we're going to do this time is talk a bit more about the consequences of these linear equations that we're solving, and then talk about Fermat's little theorem and Wilson's theorem. So Pierre de Fermat was in the 1600s. He was a French lawyer mainly, but also a very powerful mathematician. And he noticed that if you take a number and you raise it to various powers, eventually you get the same number back, modulo p. Though back then he didn't have modulo, and instead he would have written it as that p divides a to the p minus a, which is what he noticed. Yeah, so this is a very useful theorem in number theory. Another theorem that we're going to look at is Wilson's theorem, an English mathematician who, well, he didn't manage to prove it. He just noticed it. I guess he rediscovered this statement. Somebody else had found it before, but he popularized it, and then Lagrange proved it. Yeah, so Fermat's little theorem is that when you raise to a power, well, if you have a prime and you take another integer, raise that number to the prime power, then modulo p, you get the number back. And Wilson's theorem, it's this thing that's, I guess, you can use it as a primality test, but it's not a very efficient one. It's that if we have a number p that's greater than or equal to 2, it being prime is equivalent to p minus 1 factorial being congruent to minus 1 mod p. So, or if you want, that's equivalent to p mod 1. Or p minus 1. So I guess factorials, so long as you're taking the factorial of p minus 1, it vanishes. The symbol does. Yeah, this one's less useful than Fermat's little theorem, but it's a good mental exercise to explore more modular arithmetic and its properties. Okay, so the first thing that we'll talk about are multiplicative inverses. So let's say that we have a modulus n and two numbers a and b, all these integers, such that the product of a and b is congruent to 1 modulo n. Then b is called the multiplicative inverse of a modulo n. And, well, the definition says a multiplicative inverse, but what we're going to see is that they're essentially unique when they exist. They don't always exist. Because, for example, if a is 0, then nothing times 0 is going to give us 1, modulo n, I guess, unless n is 1. So here's an example. 3 times 7, that is 21, and mod 10, that's 1. So 3 and 7 are multiplicative inverses of each other. Notice because of the commutativity of multiplication, this is a reciprocal relationship. When one number is a multiplicative inverse of another number, then also vice versa, they're multiplicative inverses. Let's look at mod 6. So here's a multiplication table showing each number, well, each residue mod 6 times every other residue. So we can see that 0 times nothing gives us 1, so it is not invertible. We can see that 1 times 1 is 1. And we see that 2 we can't multiply it by anything to get 1, nor 3, nor 4. But 5 times 5, that gives us 1 mod 6. And yeah, so anyway, these are the invertible numbers modulo 6. I guess one thing to notice is that 0 and, well, let's just exclude 0. It's, well, yeah, so 2, 3, and 4 and 0, yeah, they all have a GCD with 6. That is not 1. But 1 and 5 are, they have a GCD with 6 that is 1. So we'll see that invertibility is governed by whether the number is coprime to 6 or to the modulus. Also, so 5, this is actually sort of, so 1, it's always going to be invertible because you can always multiply it by 1. But 5 here, what's actually happening is it's minus 1 mod 6. And minus 1 squared is 1. So every modulus n minus 1 is invertible, and so is 1. Well, that's a first observation. Okay, so that's the definition, still there. The next observation is uniqueness, and this is a nice little proof that I've always thought was like clever and sleek. So let's say that we have a modulus n, a number a, and 2 potential multiplicative inverses of a mod n. So the conclusion is that b and b prime, these 2 multiplicative inverses of a, are congruent mod n. So that's the sense in which they're unique. Like, there's infinitely many, actually, because we can add multiples of n to b to get lots of them, but they're all going to be congruent to each other. So here's the calculation. So we start with b, and then we rewrite it as b times 1. And then we substitute in a clever value for 1, and that is a times b prime, because b prime is a multiplicative inverse of a, so we can do that mod n. And then we can reparenthesize this, so it's a times b prime, but b is a multiplicative inverse of a. So mod n, we can replace it with 1. And 1 times b prime is, of course, just b prime. So then by transitivity of congruence, we get that b is congruent to b prime. And that is what we wanted to show. Okay, so multiplicative inverses, if they exist, are unique. The next thing I want to mention is, when do they actually exist? And this is a very important thing to know. So let's say that we have a modulus n and a number a. Then a has a multiplicative inverse mod n if and only if it's coprime to n. So that's the exact condition under which a number has an inverse. So let's prove this. So we have this implication, this by implication here. And the right-hand side, there exists a multiplicative inverse for a mod n. That's actually just a linear Diophantine equation. Well, not Diophantine, a linear congruence. So let's just rewrite that as ax is congruent to 1 mod n has a solution. So we take this conclusion that we want to show and just rewrite it like that into an equivalent conclusion. But what we proved before is that this congruence has a solution if and only if the GCD of a and n divides the constant. So we just replace that with what it's equivalent to. In GCDs, let's see. So GCDs, they're non-negative. Also, if this GCD is 0, there's something that we should say. I'm just going to say an n is greater than or equal to 1, just to patch a potential hole. So because n is not 0, the GCD is positive, and it divides 1, and so since it divides 1, it equals 1. So then we replace this with this equivalent conclusion, but both sides are logically the same, because the GCD of n and a it doesn't matter what order you're checking whether they're divisors, so that's the same. So that's just true. Okay, so that's that statement. So now we know that inverses are unique up to modulo, and then also we know the condition under which they exist, the exact condition. So one thing I'd like to mention, in here we use some results from previous lectures. Let me just remind you how it is that you can find an inverse. So recall that if the GCD of n and a is 1, then by Bayes' identity there exists some x and y in the integers where xa plus yn is 1, which again you can find using the Euclidean algorithm. And then if we take this modulo n well, y times n is 0 mod n. So then we have x times a is congruent to 1 mod n. Hence, x that we found through this process is the multiplicative inverse for a modulo n. So, given that we know that inverses are unique up to modulo, and also that we know the condition when they exist, when that condition holds, let's write a inverse, or a to the minus 1, for that x that we get down here. So, and I'm putting the in quotes because like there are a lot of integers that could be the inverse, but they're all equivalent modulo n. So it is the. And the rule that we have with this notation is that a inverse times a is congruent to a 1 modulo n by its definition. So for example, we can calculate that 3 inverse is 7 mod 10. And that's because, well, 3 times 7, as we saw, is congruent to 1. So so that's the inverse. So so another thing is, what this notation lets us do is solve equations more algebraically. So if we want to solve ax is congruent to b mod n, and we know that a and the GCD of a and n is 1, then we know an inverse exists, so we can multiply both sides by the inverse to cancel out the a. And so if we knew what a inverse was, we could just multiply b by it and then get the solution, the unique solution to this equation. Because remember, this GCD tells you how many solutions there are. I guess one thing I want to mention is I want like primes are a special thing. They're the ones where every non-zero number has a multiplicative inverse. So let's show that. So suppose that n is a natural number that's greater than or equal to 2. So we're excluding 0 and 1, the special numbers. Then n is prime is equivalent to the property that for every integer that's not 0 mod n, so just to rewrite that, that's saying that n does not divide a, then a is invertible modulo n. So to prove this statement, I thought it was easiest to do it by cases, basically. Or not cases, just splitting this by implication into the forward and backward direction. So for the forward direction, let's suppose that n is prime, and then we want to show this for all. So then let's also suppose that a is an integer and a is not congruent to 0 mod n. So then we want to show that a is invertible. So since n is prime, then there are 2 cases for the GCD because n has only 2 factors, 1 and itself. So then there are these 2 cases that the GCD is either n or 1. When the GCD is n, then n divides a, but that means that a is congruent to 0 mod n, but we assume that a is not congruent to 0 mod n, so that's a contradiction. So that case is handled because it can't happen. Case 2, when the GCD is 1, then what we already discussed is that a is invertible modulo n, and that is the conclusion that we wanted. Okay, so that's the forward direction. For the backward direction, so we assume this whole property, and we want to show that n is prime. So suppose for all a, if a is not 0 mod n, then a is invertible mod n. That's the hypothesis. And then we're trying to show that n is prime, so for contradiction, let's suppose that n is not prime. So since we assumed n is greater than or equal to 2, then it's not 0 and it's not a unit, and it's not prime, so by definition it's a composite number. And one thing we showed a few lectures ago is that when you have a composite number, there exists a non-trivial factorization of it. So a and b, where n is a times b, and a and b are neither 1 nor n. So one thing we can check is that, well, the remainder of a by n after division is a, because it's already a remainder. It's in the right range. And it's not 0 because, well, a is not congruent to 0 mod n. And, wait, what am I saying? No, I'm pointing to the wrong thing. I'm just saying that since a is not 0, and since a is a residue, that means a is not congruent to 0 mod n. There are a few ways we can say that, or give an argument for that. So by hypothesis, a is invertible modulo n because, well, we should just mention that it's not congruent to 0 mod n, and our hypothesis lets us say that this number is invertible. So then, let's calculate. So b is congruent mod n to, we're doing this multiplying by 1 trick. So a inverse a, that's 1, which we can do because a is invertible. Then we can reparenthesize it, but a times b is n, right? And n is congruent mod n to 0. And anything times 0 is 0, so then we see that b is congruent mod n to 0. But for a similar reason, for this b thing right here, or for a similar reason involving residues and thinking about that b is already a residue mod n, then b is not congruent to 0 mod n. And that contradicts what we just calculated. So we reached a contradiction. So n is actually prime, which was what we wanted to show. Okay, so what's so special about primes? We can divide by non-zero numbers mod n. Where non-zero numbers mod n means anything that's not congruent to 0, or mod p, where p is the prime. So if you're going to take abstract algebra, or if you already have, then I'll just mention quickly that the integers modulo p, when p is a prime, form a number system called a field. And you're familiar actually with a number of fields, like the rationals, the reals, the complex numbers. They're all things where you can divide by non-zero things. But one weird thing about integers mod p, this field, is that if you repeatedly add 1, eventually you'll get 0. Where in Q, R, and C, if you keep adding 1, it just gets bigger and bigger, goes toward infinity. But if you add p1s together, you get 0. So that's a weird thing about it. Okay, now that we've talked about multiplicative inverses, let's start talking about Fermat's little theorem. And let's explore different powers modulo 7 to try to see what sorts of patterns there are. So across the top here, I have labeled a to the 1, a to the 2, a to the 3, up to a point where I guess I got tired making the table. And so down this first column, we have the different values of a that we're considering. And they're all the residues modulo 7. So 0, all of its powers are just 0. So that's a pretty straightforward one. And then for the rest of the numbers, like 1, it's just all of its powers are 1. 2, so we have 2 squared is 4, and then 2 cubed is 1. So we can make this table by just repeatedly multiplying by 2. So 2 times 2 is 4, times 2 is 8, which is 1, times 2 is 2, times 2 is 4, and it repeats. And there's this length 3 repetition. Let's look at 3. So 3 times 3 is 9, which is 2 mod 7, times 3 is 6, times 3 is 4 mod 7. Oh yeah, one way to calculate that, by the way, if you don't like numbers bigger than 5. So 6 is minus 1 mod 7, and if we take minus 1 times 3, that's minus 3 mod 7, and then if we add 7 to it, we get 4. So again, like 4 is minus 3, and so that times 3 is minus 9, and if we add 14 to it, we get 5. Anyway, so then 5 times 3 is 1 mod 7, and then it repeats with a length 6 a group of powers. So powers of 4, we get this length 3 repetition. Powers of 5, we get another length 6. And then powers of 6, we get a length 2 repetition. Also remember 6, that's a minus 1 mod 7. So this is also minus 1, 1, minus 1, 1, minus 1, 1. You know, powers of minus 1, which you're familiar with. I'm not sure why I didn't label these with the orange blobs, but it would be the same pattern as 1. But alright, the reason I didn't was the interesting things about all the other ones is that they all end up with a 1 at some point. So, and the end of each group ends in a 1. Also, strangely, all of the lengths are all divisors of 6, and they all line up right at 6 because of that. So if you take any number to the power, any non-zero number, mod 7, to the power of 6, you get 1. So, that's what Fermat's theorem, or little theorem, is predicting. Also then, if we then take it to the 7th power, then we get the number that we started with, and then 0, it sort of happens to line up. So that's a to the p is congruent to a mod p. Yeah, so this is the thing that we're going to prove. I'm going to mention that this is actually a special case of a theorem to come that we're going to see later in the quarter, and that is Euler's theorem, which generalizes Fermat's little theorem. And I'll just mention as a preview what it states roughly. So first of all, for each n in the naturals, there's a number phi of n called the totient, T-O-T-I-E-N-T. And it has the property that whenever you have an invertible number modulo n, which remember is that it's coprime to n, then when you raise that number to the totient of n, you get 1 mod n. And a fact is, this totient, when you apply it to a prime number, you get p minus 1. So if we look at what this is saying, is that if a is not 0, mod p, so if a is coprime to p, running through all the definitions, then a to the totient, mod p, is 1. And that's one version of Fermat's theorem, a little theorem. If we multiply both sides by a, then we get the other form of it. And notice, like, the reason that these are both ways of saying the same theorem is what we saw about multiplicative inverses, which is that we can multiply both sides by a inverse if it's invertible to get the first form. But if it's not invertible, then we have the second form. And it's only non-invertible if a is 0 mod p. Okay, so that's a little preview of Euler's theorem, which handles numbers other than primes as the moduli. Let's look at an example of what we can do with this. And that is computing multiplicative inverses. So let's say that p is a prime and a is a non-zero number mod p. Then, since the Fermat's little theorem says that a to the p minus 1 is 1 mod p, and also since it's a prime, which means it's neither 0 nor 1, then we can subtract 2 from p and still have a natural number. And so the left-hand side is a times a to the p minus 2, which is congruent to 1 mod p. So that means that this a to the p minus 2 is the multiplicative inverse of a. So we get this formula, that a inverse is a to the p minus 2. This isn't really the best way to calculate it, at least directly like this, because say it's p is, some like 100-digit, or well, maybe that's too big. Even like just 17 is pretty large. And a to the 17 minus 2, you're going to be looking at doing 15 or 14 multiplications and modular reductions. So, well, there are some ways to still use it, but you're probably better off using the Euclidean algorithm most of the time. But this is a nice theoretical thing. So I'll show you how you can still use it in an efficient way. So mod 7, let's calculate 3 inverse. So according to this theorem, we can take 3 and raise it to the 5th power mod 7, and that will work. And then 5, I'm going to write it as 2 times 2 plus 1, because I'm thinking about 5 as being in base 2, and this is a way to do that. So it's 2 squared plus 1. And so it's 3 squared squared times 3. And that's a good thing because, well, 3 squared isn't so bad. Well, right, first of all, 5th power, that's going to be 4 multiplications, but now we just have to square times, which is only 3 multiplications. So we save something there. So 3 squared is 9, which is 2 mod 7. So we replace that. And then 2 to the 2 is 4. Times 3 is 12, which is minus 2 mod 7, because 14 minus 12 is 2. And minus 2 is 5 mod 7. Right, okay, so then let's just check. 3 times 5, that's 15. That's 1 more than 14, so it's 1 mod 7. So that worked. Let's do another example. Let's mod 13 calculate 2 inverse. So it's predicting it's 2 to the power of 13 minus 2, which is 11. And I really don't want to calculate 2 to the 11, although it's like 2 million something. It's not so bad, but let's use our methods that we have to speed this up. So base 2 means to write the number as a sum of powers of 2. So here's 2 to the 0, which is 1. Yeah, so 8 plus 2 plus 1 is 11. And then there's this polynomial trick, which to calculate a polynomial fast, you can sort of factor it starting from the highest power, where you keep like adding the next highest power and factoring out one more x. In this case, this is a polynomial with 2 being the variable, so to speak. So we've got 2 times 2 plus 1 times 2 plus 1. So we factored this 2 out. That's a calculation trick. So then, using this representation, we can do 2 to the 11 as 2 to the 2 squared. So then this plus 1 turns into times 2, and then we're multiplying by 2, which turns into a square, and then we're adding 1, which means times 2. So using just plain old exponentiation rules, we can turn this this expression, or replacing the 11 with that, we can turn it into that. Okay, so let's run through how this helps us. So 2 squared is 4. 4 squared is 16, which is 3 mod 13. 3 times 2 is 6. 6 squared, that's 36, which is, well, it's 2 times 13 plus 10. So we've got 10, and then we're multiplying by 2. Let's do that other trick again. Instead of taking 20 and, well, actually, no, 20 is fine. 13 plus 7 is 20. Okay, so then let's just check. So 2 times 7, that is 14, which is 1 more than 13. So it really is the multiplicative inverse. Let's look at one more example, which is one that it's more of a theorem, and it's one of the reasons that this Fermat's little theorem is so useful. So if p is a prime, and if a is not 0 mod p, then for n in the integers, a to the n is congruent mod p to a to the taking the remainder of the exponent mod p minus 1. So before we had rules for reducing the base of a power mod p, and so when we have a prime, we can reduce the exponent mod p minus 1. So that's our additional rule that Fermat's little theorem gives us. One thing to note is I'm allowing this to be an integer, and when n is negative, the interpretation is that a to the n is a to the minus 1 to the minus n. So we're taking the inverse that we can calculate and then taking it to a positive power, or non-negative power. So yeah, we can reduce exponents like this. So here's a sketch of a proof, because I'm not being too careful about this minus business, but if we believe the rules, that the rules should work out the way we'd hope that they do, then this is sort of a proof. But at least it gives you the idea. So let's let q be the quotient of n by p minus 1, and let's let r be the remainder after division. So then a to the n is just equal to a to the q times p minus 1 plus r. That's the division algorithm. And then using exponentiation rules, we can rewrite this as a to the p minus 1 to the q. That's the product rule turning into a succession of powers. And then the plus turns into a to the r. And then using Fermat's little theorem, because we assume that a is not 0 mod p, we can replace it with 1 mod p. And then 1 to the q is 1, right? So we got a to the n is congruent mod p to a to the r, which is this statement right there. Yeah. So now it's time to prove it, and I'm going to actually give multiple proofs. Each of them shows how to prove it in a slightly different way. And I guess we proved it already, but using stuff that we haven't seen yet, which is Euler's theorem. So let's do the quick proof, which I'm not expecting you to understand. This is just, if you've seen group theory, then you'll be like, oh, okay, I see that it's true. And also, actually, as a side note, when I was first learning this stuff long ago, I remember trying to look it up on Wikipedia, and this was the only proof that they had. And I was just like, I don't get it. I don't even know what groups are. But anyway, now that I know what groups are, I think it's a very nice proof. It's very quick. Okay, so let's look at the proof. Let's say p is a prime and a is a non-zero number modulo p. Then if we take the set of integers mod p, they form a group. Let's call it G, where we use multiplication and division of numbers mod p as the composition operation and the inverse operation for the group law. And the order of this group is p minus 1, because their number of residues that aren't 0 is p minus 1. So the order of an element is the least positive number such that a to that number is congruent to 1 mod p. And so by Lagrange's theorem, what happens is that the order divides p minus 1. And I guess just for those who like groups, what happens is if you take all the powers of A, they form a subgroup of G, and then the order of that subgroup is n, and n divides the order of the group G. So Lagrange's theorem gives us this, and then because it divides, then there's a k in the natural numbers using the definition, where kn is p minus 1. And so we can calculate that a to the p minus 1 is a to the kn by substitution, and then use the exponentiation law to say that it's a to the n to the k. But a to the n, because it's the order, is 1 mod p, and 1 to the k is 1. So that is the proof that way. But let's do a more elementary proof. This one is a cool one, and it's going to take a few slides to actually get through it because it takes 2 lemmas. But it just involves manipulating polynomials, and also we see a nice additional thing we can do with modular arithmetic on the way. So Euler's proof is that, so first of all, we need to study the binomial coefficient. And this is also one of the reasons I had the binomial coefficient on the first homework. So if p is a prime and k is a number strictly between 0 and p, then the conclusion is that p choose k is congruent to 0 mod p. Or in other words, that p divides this binomial coefficient. So how do we prove this? So we use the, I guess, well, it depends on what the definition is, but at least for us, in the homework we defined the binomial coefficient to just be this quotient of p factorial by k factorial times p minus k factorial. And so since this is true, then we know that p factorial is the denominator times the binomial coefficient. So one thing that we know is that p divides p factorial, because p factorial is 1 times 2 times 3 all the way up to p. So there's a p factor in there, so, p divides it. Then, since p divides p factorial, that means it divides this right here, this product of three things. So, because p is prime, whenever p divides by the primality property, whenever it divides a product, it has to divide at least one of the three. So that's the conclusion that this is the additional thing that we now have on hand, that either p divides p factorial, or p divides p minus k factorial, or it divides p choose k. But something that we have is that p does not divide k factorial, and also p does not divide p minus k factorial. And the reason for that is that, well, k is strictly less than p. And all the prime factors of k factorial consist of only primes that are less than or equal to k. So p, being bigger than k, does not show up among all those factors, so it can't divide it. And the same goes for p minus k, because since k is bigger than 0, then p minus k is less than p. So, since it divides neither of the first two in this disjunction, it has to divide the last one, which is exactly what we wanted to show. Okay, so when you have binomial coefficients, where the top, or where it's a prime choose something, if the something is neither the beginning or the end of the range, then it's divisible by p. That is a key fact for us. Now we need another lemma, sometimes called the freshman's dream. So suppose that p, a, and b are natural numbers where p is prime, and then the conclusion is that if you do a plus b to the pth power, then mod p, it actually just equals a to the p plus b to the p. It's the algebraic rule that back in pre-calculus or calculus that you just really wished were true to make manipulations easier. But, so long as it's prime and you use p as the power, it is true. So to do this, we need to recall the binomial theorem. A plus b to the pth power, according to the binomial theorem, is the sum over all k between 0 and p inclusive of p choose k times a to the p minus k, b to the k. So that's I'm just stating the binomial theorem. So we have the sum over all 0 inclusive on this interval. So we can make the interval exclusive and pop off the k equals 0 case and the k equals p case, leaving this inner part. So mod p, we have a to the p plus, and then in the sum, we have p choose k, which according to this lemma is congruent to 0 on this range. So we can replace it mod p with 0. And then after that sum, we have b to the p. And 0 times anything, of course, is 0. And a sum of zeros is 0. So we get that this left-hand side is indeed congruent mod p to a to the p plus b to the p. Okay, so that is our second lemma. And now that we have these two lemmas, we can continue with the proof, and it's very straightforward. It's a simple induction. So, like before, let's say we have p and a being in the natural numbers where p is prime. Then we're going to show that a to the p is congruent to p mod a. It's congruent to a mod p. Right, so we're going to do induction on a. And the base case when a is 0 is simply checking that 0 to the p is congruent to 0 mod p. And 0 to the p, that's 0. right? So it's just 0 is congruent to 0. That's reflexivity. So the next one is the inductive step. So we suppose that it's true for a given A, and we want to show that it's true for the next A, the successor A. So let's do this equationally. Equational reasoning. We have a plus 1 to the p, which by the freshman's dream is a to the p plus 1 to the p, mod p. And 1 to the p is 1, because it's just 1 times itself repeatedly. So that's the right-hand side. So we showed what we wanted to show. And so therefore the conclusion holds because we did the induction. So I want to point out that, and I mentioned this already before, but this implies the other form, because if A is invertible, then, well, a to the p minus 1 is A inverse times a to the p, and then that is equivalent mod p to A inverse times A by what we just showed in this theorem, and A inverse A is 1. So that's the other form of Fermat's little theorem. And so that's if A is not congruent mod p to 0. Now it's time for the third proof. And this one is the Ivory / Dirichlet proof. I guess Ivory found one, the world forgot about it, and Dirichlet came up with one again, using basically the same techniques. This is the one that shows up in the textbook. So the first thing to observe, and also this is a nice one because it gives us some more idea of the structure of numbers modulo p. So let's look at these multiples of A. We have A, 2A, 3A, all the way up to p minus 1A. So we're starting with 1A, of course. So the fact is that this list of numbers, modulo p has no repeats. So how do we show this? Well, let's say that there was a repeat. So for some C and D, CA and DA were congruent mod p. So since A, we're assuming that A is not congruent mod p to 0 for this. So that means that it's invertible. So we can multiply both sides by A inverse, and then that gives us that C is congruent to D mod p. But if C and D are coefficients for this list, so that there's 1, 2, 3 up through p minus 1, then certainly it lies within 0 inclusive and p exclusive. And something we mentioned a few lectures ago is that when we have a congruence of residues, then it's an equality. So that's why there are no repeats. Because if they repeated, well, it was actually the same number. If they repeated, they didn't actually repeat. You just didn't realize your fingers were pointing at the same number. So another fact is that none of these numbers are 0 mod p. And the reason for that is we can reuse the previous work. If one of these numbers were 0 mod p, then we can use 0 for D. And then, since that's in the right range, then C would be 0. But 0 does not show up in this list of coefficients. It's only 1 through p minus 1. Okay, so there are no repeats. 0 does not show up. So what that means is that if we take all the residues of all these numbers, all p minus 1 of these numbers, then by rearranging them, we get just the numbers 1 through p minus 1. We get all the residues that are not 0, all p minus 1 of them. So now we do some magic calculations. So consider p minus 1 factorial times a to the p minus 1. So p minus 1 factorial is the product of 1 through p minus 1. And then by taking these two numbers and I think the word is intercalating them, So we can then write this as 1 times a times 2 times a times 3 times a, and so on. So each of these p minus 1a's gets a partner among the factors of the factorial. And then by this observation that the residues of these numbers encompass exactly the list of non-zero numbers mod p, we can rearrange it and replace them with those residues mod p, and that is p minus 1 factorial. So notice that we have p minus 1 factorial times a to the p minus 1 is congruent mod p to that same factorial. Now here's the observation that makes this then all actually go somewhere. Notice that p does not divide p minus 1 factorial. And that's because p is bigger than p minus 1. So p minus 1 factorial just doesn't have p as a prime factor, or a prime divisor. So that means that it's invertible mod p. And so we can multiply both sides by the inverse of it mod p to get exactly what we want, which is Fermat's little theorem. Okay, so one thing in here. Okay, yeah, so now we've proved it 3 ways, but one reason to show this proof is that inside this is this p minus 1 factorial, and here we just said it is invertible. So there's this question, which is, well, it's invertible, but can we just figure out what it is? And that's sort of what Wilson's theorem is about, just to let us know, like, what did we do here? So the theorem is, if we have a natural number that's at least 2, then this p minus 1 factorial is actually just minus 1 mod p when p is prime. But also, if it is congruent like this, we can also say that p is prime. So this gives us a sort of a primality test, but like, how do we show that a number is prime? Like, one way is just to go through all the check and do trial division and divide it by every number 2 through p minus 1. And really, like, do we really want to be calculating p minus 1 factorial mod p? Like, is that really any better? No, but anyway, it's this, like, it's a nice theoretical result there. So let's, by way of example, let's prove it, and then we'll actually prove it. So when p is 7, 7 minus 1 factorial is 1 times 2 times 3 times 4 times 5 times 6. And then let's look at the inner numbers. So one thing we can calculate mod 7 is that 2 inverses 4, 3 inverses 5, 4 inverses 2, and 5 inverses 3. So they come in these pairs. And so since they come in these pairs, what that lets us do is we can rearrange them so that like the 2 and the 4, we can put those next to each other, they're inverse pairs, and the 3 and the 5, we can put those next to each other, and mod 7, that's 1. And so we're only left with, well, the first and the last number after multiplying it all out, and the first number is just 1, so really we're left with the last number. But that last number is p minus 1, or 7 minus 1, which is 6, and that's minus 1 mod 7. So that's why that's true, at least in this case. We need one more ingredient to be able to prove Wilson's theorem, and that is that all those inner numbers in the factorial are not inverses of themselves. We want them to not come in pairs. I mean, like, we want them to come in pairs without, without pairs of 1. So here's a lemma. If p is prime and x is an integer such that its inverse is itself mod p, then the conclusion is that x had to have been plus or minus 1 mod p. So, or in other words, it's either x is congruent to 1 or x is congruent to p minus 1. Just to relate it back to factorial for that second one. and it's a fairly straightforward proof. So let's suppose that p is prime and x is its own inverse. So we can calculate the x squared. Well, of course it's x times x, but using this hypothesis, it's congruent to x inverse times x, and x inverse times x is congruent to 1, because it's the inverse. So, using the definition of congruence, we have that p divides the difference of x squared and 1, and since x squared minus 1 factors is x minus 1 times x plus 1, and p is prime, by primality, p has to divide one of these two factors. But translating those back into congruence notation, it's that x is congruent to 1 mod p, or x is congruent to minus 1 mod p. So that's exactly what we wanted to show. Now, given that, let's prove the first part of Wilson's theorem, which is that if p is prime, then p minus 1 factorial is indeed minus 1 modulo p. And there's a lot of cases in number theory where we have to treat the oddest prime 2 especially, and this is one of those. So when p is 2, then we can just check it, right? So 2 minus 1 factorial, that's 1 factorial, which is 1, and mod 2, that's minus 1. Case 2, when p is an odd prime, so when it's a prime greater than or equal to 3. So writing p minus 1 factorial using an ellipsis, so 1 times 2 times 3 times dot 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 times the rest all the way up to p minus 1. Then starting from 2 and ending at p minus 2. So there are p minus 1 factors total, and we're throwing away 2 of them for this braced part, and that gives us p minus 3 factors here. And since 3 is odd and p is odd, their difference is even. You know, we take this mod 2. So p is 1 mod 2, 3 is 1 mod 2. The difference is 0 mod 2, so it's even. So one thing is, the inverses of each of these numbers in the middle are not 1 or p minus 1, and that is because 1 inverse, as we said before, is 1, and p minus 1 inverse is itself. So by uniqueness of inverses, then, nothing in here has those as inverses. Also, by the lemma, each number's inverse is another number from this list. So the p minus 3 factors in here, there's an even number of them, and so they must come in pairs where each number has an associated friend that's its inverse. That's different from itself. So by then pairing them off and then canceling them out modulo p, then p minus 1 factorial is 1 times and then however many pairs there were, which is half as many factors as there were. So we get all those 1s, and then we have the p minus 1 left over at the top. And all those 1s, that's just 1. And p minus 1 is minus 1 mod p. So that's Wilson's theorem. So by understanding multiplicative inverses and like which ones are their own inverses, we're able to prove it. So back in Fermat's little theorem, the Dirichlet proof, then this p minus 1 factorial that shows up, so it's invertible. Sure, it's invertible, but it's also just minus 1. So, and minus 1 is definitely invertible. Okay, so the second half of Wilson's theorem is we want to be able to conclude that p is prime if this congruence actually holds. So let's suppose p is a natural number that is greater than or equal to 2, and that congruence holds. So what we do is, so let's take this congruence and rewrite it in division form, or divisibility form. So p divides p minus 1 factorial plus 1. And so we want to show that p is prime. So because p is greater than or equal to 2, we know it's not a unit already. So we can use the indivisibility property of primality to prove it. So it suffices to show that if A is a divisor of P, then A is 1 or P. So let's suppose that A is one of these divisors, and let's rewrite this OR into something logically equivalent. So it suffices to show that if A is not P, then A is 1. Because this is just another way of stating a disjunction. So let's suppose now that this hypothesis holds, that A is not P. So we're going to show that A is 1. So since A divides P and P divides this sum, by transitivity of divisibility, which we proved a while back, A divides that sum. And also, remember, when we have natural numbers with divisibility, we can weaken it into an inequality. So A can't be bigger than P. So we assumed, though, that A is not P, so it's not equal, so it's actually strictly less. And then also, since it's strictly less, that means it's less than or equal to P minus 1. So it actually shows up as one of the factors in the factorial. So it definitely divides it. And so since A divides this P minus 1 factorial, and it also divides this sum of that factorial with 1, it divides the difference of the two by the linearity property of divisibility. And the difference of the two is 1. So A divides 1. And since A is a natural number, A is 1. Okay, so that's why P has to be prime if this property holds. So in summary, we talked about multiplicative inverses, we talked about how they're unique, and we talked about when they exist, and we gave notation for them, A inverse. And uniqueness is only, unique modulo the modulus. Then we talked about Fermat's little theorem and gave a few proofs of it. And then, I guess following up on that P minus 1 factorial that showed up, that was purportedly invertible, we actually figured out that mod a prime, it is minus 1. So it's definitely invertible for that stronger reason. Okay, so... Yep, so that's it for today, and I'll see you next time.